Hello everyone, we are from group B22 and our project is on Through the Wall radar. Our chosen antenna for Through the Wall radar application is this low profile directional ultra-wideband antenna. This is a design created by Dr. Zhu and we are going to use this design for our simulation.
This antenna is not used commercially, but a prototype has been created for experimentation purposes. So the figure here is a schematic of the antenna. Figure A is the top view, and the gray circle in the middle is the radiator. It increases impedance matching at high frequencies, and its radius affects the reflection coefficient. Figure B shows the bottom layer of the antenna, and you can see a fork-shaped tuning stub. This is the feed line, and having the feed line at the bottom layer causes this antenna to have a better impedance match at lower frequencies. Some antennas only have a radiator at the top but no feed at the bottom, or vice versa. And this antenna has both, and this results in an increased impedance matching. And because of this good impedance matching, the gain of this antenna is 4 to 6 gigahertz.
This is a prototype of the antenna. The prototype is fairly small, and the brown circle in the middle is the radiator. It's about 7.5 millimeters in size. The graph here shows the different measured and stimulated reflection coefficients over different frequencies, measured by the researchers at the University of Surrey, and they're the team that fabricated this antenna. This antenna features a reflection coefficient below negative 10 decibels over the frequency range from 4.1 to 8.9 gigahertz, which covers the desired frequency band of 4.2 to 8.6 gigahertz, given by the Office of Communications.
I will now be talking about the geometry of the ultra-wideband antenna. Dr. Zhu and his associates decided to create two separate antennas to see how they would work independently, but ended up combining them both together. The first antenna design is composed of a rectangular sheet of copper of width 30 millimeters and length 34 millimeters. A circle of radius R1, 13.7 millimeters, was cut out of the copper sheet along with a rectangular wedge of width 4 millimeters, which is lowercase w plus 2 times the gap g, and length lowercase l 5.45 millimeters. This antenna design incorporated a planar circular patch of radius R2 7.5 millimeters and a handle of width lowercase w 3.6 millimeters and length lowercase l 5.45 millimeters. The center of the circular patch is 5.3 millimeters below the center of the circular slot, indicated by X. The gap G is 0.2 millimeters. This design was implemented for field manipulation. However, this design was not good at impedance matching at low frequencies. This was the second antenna design implemented by Dr. Zhu and his associates. The only change made is now instead of a planar circular patch and handle, we have a planar fork sub with a handle. The handle is of width lowercase w 3.6 millimeters and length lowercase l1 of 9.5 millimeters. On the prongs of the fork, the dimensions are T1 equals 7.5 millimeters, T2 equals 4 millimeters, and T3 equals 0.4 millimeters. The gap G is still the same, 0.2 millimeters long. This design was implemented for field excitation. However, this design was found not to be good at impedance matching at high frequencies. Dr. Zhu and his associates decided on a combined antenna, a three-layered antenna where the bottom layer was composed of antenna 2, and the top layer was a simple circular patch placed 5.3 millimeters below the center of the circular slot, shown by the X value. These two layers were separated by a 1.575 millimeter thick sheet of duroid substrate of width 30 millimeters and length 34 millimeters to fully cover antenna 2. The overall antenna was designed to be small and cost-effective as well as portable and be good at impedance matching at both low and high frequencies, which the other two antennas weren't able to do separately.
I'm just going to talk about the OpenEMS implementation that we use for our through-the-wall radar, and the tutorial that we found the most useful when writing the code for the simulation was a simple patch antenna that we found from the OpenEMS website, and we adjusted this example according to the specifications given in the article. So we begin by setting some constants. So the first constant is the center frequency for simulating the antenna, which we were able to find in the article. And the next constant is the corner frequency for the broad bandwidth. And the last constant is conversion between meters and millimeters to make it easier when we're writing the code for the simulation. Next, we initialize the finite difference time domain to be used in the simulation by setting a maximum number of time steps, applying a Gaussian excitation, and adding boundary conditions for the simulation. And the end criteria here is to stop the simulation when energy has decayed by -50 decibels. The next step is to add the geometry, and we begin by initializing a grid to be used for the shape. Next, we add 3 different materials to be used in the simulation: metal, air, and the dual-rate substrate. And we added the air material to make it easier to create the complicated shapes of the antenna. And the dielectric constant epsilon for the dual-rate substrate was set according to the specifications given in the article, which was 2.2. Now that we have all the materials, we can now create the geometry by adding simple rectangular boxes and cylinders together. And notice that over here I have commented out this part, because that is where we're going to be applying the excitation as a current source, starting at the bottom of the fork of the antenna and moving up. And now we can write to a .xml file to be used by OpenEMS, and we can show the structure using CSX. And now we can do some post-processing to be used for the plots. And the code for all of this was found in the simple patch tutorial. And some of these post-processing include finding the input impedance and the antenna feed power. So here's the code for plotting the feed point impedance and the reflection coefficient. Before plotting the near field to far field contour, we must first find the resonance frequency and then calculate the far field at phi equals 0 and at phi equal 90 degrees. Finally, we can now plot the normalized directivity as a polar plot and as a log scale directivity plot. And we can also plot the 3D far field pattern using a log scale.
Hi, so I will be talking about our simulation results. Let's talk first about the simulated feed point impedance. Feed impedance is the impedance of the bottom of the fork-shaped structure, and in our simulation parameters, we set the feed impedance to be 50 ohms. There is some deviation from this value over the large frequency range, but resistance does approach 50 ohms at higher frequency. There is an imaginary component due to the inductive effects. Second, we'll talk about the 3D electrical far field. The 3D electrical far field pattern for our simulation shows good gain characteristics at 8.14 GHz. The gain is approximately evenly spread, which is important because a uniform field is necessary for through-the-wall applications. Okay, so on to the simulated reflection coefficients. The simulated reflection coefficient from the research paper shown on the left and our own simulation shown on the right both follow the same general pattern of decrease from low to high frequencies. In our case, our simulation gives a much simpler monotonic decrease because we used a perfect conductor model for the metal sheets in the antenna instead of modeling the metal's imperfect permeability and permittivity as the research paper did. The research paper's proposed antenna simulation shows good impedance matching when the reflection coefficient is most negative, and that would be in the range 4 to 6 GHz and around 7.5 GHz. And lastly, we also simulated the normalized electrical far field.
In the case of the research paper, they didn't normalize it, so that's why you would see much larger values over there. Our simulated far field in polar coordinates matches well with the research paper's measured results, especially in the H-plane, which would be at phi equals 90 degrees. And again, the perfect electrical conductor estimation of metals we made in our simulation resulted in a much simpler E-plane far field pattern at phi equals 0 as compared to the research paper. And that's it for our presentation. Thank you for watching. Please like our video and don't forget to subscribe to stay updated with our project. We've made a lot of progress and we hope you're going to follow up to the end.